DC converters. Now, in the AC-DC converter, before you start, then we may need to actually make something clear to you. Okay, for example, this one, the F is called the fundamental frequency. Fundamental frequency for a power supply is actually either 50 hertz or 60 hertz. Now, in Malaysia, we are actually using a 50 hertz base. Okay, in other countries like Japan, USA, for example, they are using 60 hertz base. So their voltage is actually running somewhere at around 110 to 120 volt. But in our case here, where you are running 230 to 240 volt. Last time used to be 240 volt, but already revised. Our voltage is at 230 volt. And also in China, if I'm not mistaken, China, they are using 220 volt. So still, the product that made from there, we can still use. Yeah. All right. Apart from that, we also have this omega. Omega is the frequency in radians. So if I have F, if I have the frequency is F, so my omega will be 2 pi F. So we multiply by 2 pi to the frequency. That will give you the this frequency in radians. Okay. Then T normally is the period. Okay. Normally we have the T measured in second. Okay. So the T is actually the reciprocal of the frequency F. Okay. So this is the relationship between there's few unit there. Right. So in this chapter here, you will also see that we are going to look into the uncontrolled tap. Uncontrolled tap normally is covered under this chapter 3. The control tap will be covered under chapter 4. Similarly, we will also look into the single phase system and also the 3-phase system. Yeah. Of course, for simplicity, okay, when we are looking to the example or from the teaching material here in this lecture notes here, normally we assume that there will be no TRR and also there will be no voltage drop VD. Okay, TRR is a reverse recovery time. Still remember for of a diode. Okay, so we assume that it is ideal. Okay, no such thing. Yeah. All right. Also, I need to introduce you with some performance parameter. Those parameter is actually very important for you to measure given systems. Okay, it can be actually used to measure or calculate the input and output value. For example, in this slide here, you have the output DC power P out DC. Okay, because after the rectifier, your waveform become a DC, even though there's a ripple, but all are actually having a positive value. Okay, so this is the average. The average is actually equal to the V out times your I out. Okay, output DC voltage and AC currents. Okay, in short, normally we just write PDC equal to VDC times IDC. Okay, we do also have another quantity called the P out AC. This P out AC is in fact the RMS output power. Okay, RMS output power is actually determined by multiply the RMS voltage and the current together. Okay, so that makes a difference between the DC power and also the RMS power. Yeah. We do also have the efficiency. Efficiency is determined based on this formula here. This efficiency is called the rectification efficiency, the rectifier's efficiency ratio. Okay, so it's determined based on the PDC over the PAC, PLAC. Okay, so normally it's in percentage. You have to multiply by 100%. Yeah. Okay. Now, you know that in a given this waveform, for example, the voltage waveform here, okay, say the IMS normally, the output IMS normally comprises of the what is so called the DC and also it is ripple. Okay, so that makes the difference between the DC and also the IMS value. Okay, so that's why. But sometimes when it comes to very high efficiency type of these rectifiers, especially in a three-phase system, you can see that the ripple factor become very less significant because the DC value could be almost equal to the IMS value. Okay, so we will actually look into it later on. Okay, so you don't need to worry too much on that thing, but you just need to remember we have two value. One is IMS value, the other one is the DC value. Yeah. Form factor. Form factor is the unit to measure the shape of the given quantity. For example, we have the voltage. This form factor. We do also have the current one. Yeah. The form factor FF here is actually equal to the ratio of the IMS value over the DC. Yeah, the same thing applied to the ripple factor. In this case, I'm using only the voltage as an example, but we do also have the current ripple factor. Yeah, they are in fact equal to the IMS value over the output DC. So which is the ripple. Okay, so but after you do some kind of substitution based on this relationship here, the equation here, you can see that your ripple factor here is in fact equal to your form factor square minus 1 square root 2. Yeah, this is how I get this thing. Okay, all right. Now, current ripple factor, similar case, similar to the one with this voltage ripple factor. Okay, they are also equal to the IAC over the IDC, but just that it is in current. Yeah. Now, VRPP is actually a peak-to-peak AC ripple. Okay, so if normally we do also have a quantity called VPP, peak-to-peak. I believe you have already seen it. Yeah. Then the VRPP can actually obtain based on this formula. That means that I have my output load current maximum value minus the minimum value. That should give me the peak-to-peak value. Okay. TUF is called the transformer utilization factor, which is equal to your output DC power over the watt ampere rating of your input. Okay. If your system is actually using a transformer, that means that your transformer secondary will be your input to measure this TUF based on the rectifier they attached to. Then you get the DC output from your rectifier side, and then you get the watt ampere rating from your secondary of your transformer. Okay. Normally these two quantity, they are normally in IMS value, root mean square value. Yeah. This is what is so called the watt ampere rating. Okay, VA. Okay, normally we should just put VA. Yeah. Now, this figure here shows you the supply voltage VS here, and then we do also have the supply current or the input current. If normally because supply, yeah, they have the inductor, and also if our load is having a very high inductive inductor, okay, you see that this current tends to become a square wave. Okay, so if you are I don't know whether you got study some sort of numerical method or not. You can actually derive your this square wave, okay, based on all your this sine wave add up together. Okay, the order, the harmonic order, 1 until maybe 100 or 200, depend on the accuracy percentage. Okay, so when you add up everything together, it becomes a square wave. So this is the same thing. Okay, in this figure here, it shows you the dotted sine wave here is in fact your fundamental fundamental current IS1. Okay, at 50 hertz. Okay, so this one is actually extracted from your this square wave. Okay, and as you can see that if the load is no longer a linear, no longer a linear or non-linear load, meaning that your load is having capacitive or inductive this value. Yeah, so you actually make your current no longer be in phase with your this voltage. Okay, so when you extract your this fundamental, you can see that they are not in phase to your this voltage waveform. Okay, you can see there is angle difference called the phi here. Okay, called the phi. Yeah. So for further this description or understanding, we'll do it one by one later on. Yeah, but this one just for general. Huh? Okay. Sometimes the phi here or the angle difference between the voltage and current waveform is also called the displacement angle. Yeah, displacement angle. Yeah. Now, if we have the IL load, okay, then you can see that the angle phi here can be obtained based on this formula here, so that we have the inductive load, IL load, so that the arctangent of omega L over R should give you the displacement angle phi here. And we do also have another factor called displacement factor. Displacement factor, dF is equal to cos phi only. The phi is actually this one. Okay, so this is also we also call it as a fundamental power factor. Okay, so that is why normally some of your study, you can see that the power factor equal to cos theta, okay, or cos phi. Okay, so this one is actually without the consideration of other, but just consider the phase angle difference between the voltage and the current waveform. Okay. So the next one is called the harmonic factor HF or THD, total harmonic distortion. Total harmonic distortion is actually a quantity to measure how much the distortion of a given waveform it has. Okay, especially if your load is actually non-linear. Normally, most of the time, your current waveform no longer a sine wave, so you tend to have a very high THD value. Normally they are in percentage. You need to multiply by 100%. Okay, so it can be actually formula as this. Okay, your total current, okay, or your supply current over your fundamental supply current, holding square and then -1, and then the entire term square root 2 multiplied by 100%. Okay, now THD can be used to measure the current and also the voltage. Okay, we have the THD I for current, THD V for the voltage. Yeah. Now, input power factor. Now, input power factor or the power factor, you can see that if in general is supposed to have this equation here, your VS IS1 over your VS IS times cos phi. So if, for example, I have my load, which is a resistive load. Okay. Normally, you can see that there is no the cos phi here. It will equal to 1 because your phi here is 0. So that should actually only determine the power factor should be actually equal to the ratio of your fundamental over your IS. And believe me, if your load is resistive, you can see that your IS1, the value will be very close to your IS. Okay, so this power factor could be very, very high. Okay, theoretically, it's supposed to be give you 1, the maximum value. But in practical, you never get 1. Okay, you get 0.9 something. Okay, but you won't get 1. Okay. Another quantity is called the crest factor. Okay, which is equal to your peak over your IMS value. So normally you're supposed to have, ideally you're supposed to have square root 2 there. Okay, square root 2. Okay. But of course this one is very subjective if according to a given system. All right. So here, this one here, for given ideal rectifier, okay, you're supposed to have this set of measure values. Okay, your form factor equal to 1 because DC equal to IMS. Your efficiency must be 100%. That means that there will be no losses, and hence your output DC and your AC is the same. Okay. You also do not have the ripple factor. Ripple factor is 0. TUF is 1. Okay. The value of TUF determines the rating of your transformer. The higher the value, meaning that your the rating of your transformer must be high enough in order to make it work properly. Yeah. Okay. But the ideal one is equal to 1. Okay. In here, it tells you that if TUF is 1, meaning that your DC output power is then equal to your watt ampere rating, okay, of your input. TSC is 0 if your IS1 equal to your IS. Okay. This one basically is impossible equal to 0. Okay. It's impossible. Yeah. And then we do also have the power factor or the DPF. DPF is called the displacement power factor. Okay, displacement power factor is equal to 1 for ideal case because there will be no phase difference between the current and the voltage waveform. That is why your phi equal to 0. So cos 0 give you 1. Okay. All right. So far so good. Anything you would like to ask? So far, okay? Oh, good. Very good. Great. Okay, no, then we boleh tahan. We go to next slide. Now the next slide just to let you know that you need to understand this, the Fourier series and the symmetric. Okay, so I may have this formula for you during the exam, the final exam. Okay, but you need to understand how to actually derive given Fourier coefficient, the AN, BN, and also the AO term. Okay, be it like whether it's the odd function, even function, half-wave symmetric, and or even a quarter-wave symmetric. So how will it be? Okay, all those things you got to be understand. Yeah. Okay, I will not go into it for you because this one is under your mathematics. Yeah, you should have already studied this before. Okay. Now, just an example, a sine wave. A sine wave is actually depend on the input or the output you measure. If it is the input, you are measuring at the input. So your input sine wave for a given rectifier is supposed to be a function. Okay, but when it comes to for full wave rectifier, if it is at the output, then your output should be an event function. Okay, because you rectify, the value is actually multiplied by 2, right? Okay, so please get ready for your this skill. Okay, the Fourier series. Fourier series is very important in this subject here. So you need to know. Okay, so now let us go into the rectifier. Okay, maybe in the beginning here you find it very simple. Okay, be it simple, but hopefully you can understand. But as long as you go through the rest of the chapters, then you get a little bit hot, then hotter. Okay, but you need to drink some herbal, okay, to cool down and then continue. All right, in this single phase uncontrolled converter here, basically we can divide this uncontrolled rectifier into two types. One is called a half-wave rectifier, the other one is called a full-wave rectifier. Yeah, half-wave and full-wave rectifier. Okay, so let us take a look on the half-wave rectifier first. So half-wave rectifier could be very easy. Okay, so what you need to do is that you just need one diode to connect between the supply and the load. Okay, to make it simple, let us start with the resistive load. Okay, if it is a resistive load, if I have the diode connected in this direction here, that means that when for the first half cycle, when it is positive, that means that the current is flowing in this direction. Okay, the current flowing in this direction. Okay, so if the current flowing in this direction, the diode D1 here is in forward bias, so that there will be a current pass through or flow through the D1 and then go to your resistor R here and then return to Vs negative. Okay, so this is say your input. So we measure here your Vs waveform. So it's a sine wave. So when you are measuring at the output here, you for the first half cycle, you also measure some similar wave shape. Okay, this wave shape depends very much on the resistor. Okay, so so if you have high resistor value, this value could be quite equal to your this Vs lah. Okay, if it is low value, then this could be lower slightly. Okay, and the same thing if it is a resistive load. So the current waveform must be follow the voltage waveform. So as your load current here. So if you are measuring the load current here, okay, which is your supply current, because your load current here is actually in series to your IS. So they are the same. So that is why in this graph here, we shows you only the supply current IS, which is equal to your Vm over R. Okay, so if we are actually measure it, we also measure a ripple, very fine ripple, some sort like that, which is similar to your voltage waveform. Okay, and again, the current IS here or your load current here is depend very much on the value of the R. If your value of R is big, this value, your current will be, the magnitude will be low. If your R is less than 1, you can see that you have a very high value for your current. Yeah. What happened when I'm measuring the voltage across the diode D1 here during a pulse up cycle? If I place my probe here, positive here, and negative here, do I measure anything? We measure nothing, because during this period of time, during this half cycle from 0 to pi, so the current is actually flow through. So the diode is in forward bias, so it's conduct. When it's conduct, we assume that when the diode is conduct, it act like a wire. So you measure this point and this point, you are in fact measuring two different points through the wire. The wire, normally we assume that no resistance, so that you measure nothing. However, in the actual reality, for a given diode here, you should actually measure a small value across it, okay, during this period of time. This is actually the threshold voltage that enable the diode to actually turn on. Okay, so we ignore this part for now. Okay, we assume that it's 0. Okay, this threshold voltage depends very much on the material that you use. For example, if I'm using the silicon, we have somewhere about 0.7 volt of the voltage drop across, and also depend very much on the rating of your this diode. If the diode is normal and small rating type, normally you should get somewhere about 0.6, 0.7 volt. But if it is a higher rating, you may see that they should be 2, 3 volt, for example, okay, across it. Yeah. Then from pi to 2 pi, when your this waveform is actually reached to pi, then your this waveform it become negative. Okay, from pi to 2 pi, it become negative. That means that the current is actually flowing from a Vs negative to the R to the D1, and then go back to Vs negative in this direction. Okay, which is opposed from the previous 0 to pi. Okay, when during this period of time, you can see that the diode is now under reverse bias, so that there will be no current flow through. Because why? Because the diode is in reverse bias. Okay, so there should be no current flow through. However, do I measure any voltage across it? If this one already, yes, positive cycle is forward bias, negative is reverse bias. Okay, so you measure nothing here because this one already open. So you measure this point to this point, you are in fact measuring the same point, the same line here. Okay, so there will be no potential difference. Okay, this one for circuit analysis, you also study. Okay, if the circuit is open, when you measure this point and this point, you should ignore this resistor, right? Because you are measuring uh, uh, incomplete this circuit, so you measure 0 value. Okay, so that's why there is no value here. Okay, the same thing applied to your current. If there's no, the current is actually blocked by the diode D1 here, so there will be no current. However, this time when you are measuring the voltage across the diode, okay, with the probe positive here and your negative probe here, so you can you should measure that there is a ripple, negative value of the ripple appear across your this VD. Okay, so the maximum value is also equal to the VM. Okay, so everything understand? No problem, huh? We are not looking into it. We are not actually making your rectifier to run under this avalanche region. Okay, so you don't need to be worried about it. Okay, any other? No. Now, when you are in your level 2 or level 1, okay, you may see that your lectures will actually tells you what is the output voltage VDC is equal to. For example, halfway it tells you it is in fact equal to what? VM over 2, right? VDC equal to VM over 2, right? Yeah. So what happened? Sorry, VM over pi. Vm over pi. Okay, and then what happens when it comes to here? Here we are actually doing the derivation based on the integration. Okay, so for the VDC here, we can see that okay, VDC is your average this voltage or the DC voltage output here. Okay, so we can actually we can do it integrate the time from where it's supposed to have from 0 to t. T is the period, which is a cycle. From 0 to 2 pi is actually called the period t. Okay, but when you are looking into it, your output voltage only having some value from 0 to pi only, so that you supposed to do the integration from 0 to pi only. Okay, and hence you have this one here. Then the VL is actually the load signal. Okay, the supply signal, which is called Vm sine omega t, because it's a sine function. Okay, with the magnitude of Vm. All right, so if you do the integration, you found that your VDC is in fact equal to Vm over pi. Okay, or equal to 0.318 Vm. Normally, I don't want you to remember this number. I want you to remember this one only if you cannot derive. Okay, but normally I hope that you can derive, because most of the question or some of the question are not most. I will request you to do the derivation before you do the calculation, and there will be no formula given to you during the exam. So if you don't know how to derive and you also cannot remember, you cannot proceed to the next part. Okay, so this is where the difficulty come from normally. Yeah. So if this is a resistive load, you also can see that your IDC is in fact just equal to the voltage ratio to the resistor R, VDC over R. So that will give you the IDC. All right. Now, in the IMS value, okay, we also having the same thing. IMS is a root mean square. So you have similar setup like this one for VDC, but just that your this Vm sine omega t here is actually square, and then whole thing square root 2. Okay, so if you have this formula here, you know, sine square, difficult for you to do the integration. Okay, so you may need to break it down. So you may need to use the trigonometric identity. So in this case here, I have already placed the sine omega t square is equal to 1 minus cos 2 omega t over 2 here for you. So we need to actually substitute this into here, and then only you do the derivation. After you've done the derivation, then that should give you Vm over 2, which is your IMS value. Okay. Similarly, if you want to find the IMS, you just divide the VMS by R. That will give you the value. Okay. So most important thing, if you are going to do the previous performance parameter, like for example, this one, even this one, and this one here, you need to know how to get VDC, IDC, VMS, and also the IMS, this 4 value. Once you know how to calculate this 4 value correctly, you can then work out those performance parameters that we just mentioned just now. Yeah. Now, sometimes to do the integration based on the DT here is a little bit not that convenient. Okay, because normally when our waveform here, normally we are actually refer our time as the omega t. Okay, and we are using the radian for a given period. From say 1 cycle is actually equal to 2 pi. Okay, half cycle is pi, quarter cycle is pi over 2. So we don't actually use the t, half t or quarter t. Okay, so this one is more convenient, and hence I'm not very advisable to you all to do the this time to do the integration for your this value. Instead, you may need to use the omega t, respect to the omega t, d omega t. Okay, so this is the way how I do it. Okay, for example, for the VDC, okay, I know that omega is equal to 2 pi f. So that should give you equal to 2 pi over t. And then if I bring the t to the left hand side, I have omega t equal to 2 pi. That makes sense, right? So that our integration range can also be changed from the time t to radian. Okay, so this is a more proper way to do the integration. If we rewrite the integration as for my VDC here, I have this. Okay, but of course I know that this one equal to 0 because pi to 2 pi I have no what it appear across the output. So this one is 0, and hence the equation reduced to only this term only. Okay, so if I am derive this term here, I know that integration of a sine give you minus cos, and hence I can straight away work it out. If I am do it step by step, then later I found that my VDC equal to Vm over pi. Okay, so the same thing you can also apply to derive your VMS based on this omega t. So please do it later on, yeah, for the VMS, yeah. So far, any questions? Ooh, very good. No questions. Still digesting. Can okay, good. It depends on the question. You can straight away use the formula to calculate if I'm not asked you to derive. Yeah, some question I ask you derive VDC or VMS for a given system. For example, for halfway or full way or semi-converter. Okay. So you need to derive first. If I'm not asking you to derive, I ask you to calculate or compute, then just compute based on the formula. Okay, if I'm asking you to derive, you do not do the derivation, straight away give me the answer, the formula, and then do the calculation. Your derivation part will be omitted. The point, yeah, the point will be omitted. Now, just give you an example. If I have the derivation and calculation together, derive then calculate. Okay, say if I'm giving 6 point, 4 point will be go for the derivation, and only 2 point for the calculation and the correct answer. Okay, this is the way how I do marking. Okay. All right, no question. Then we go to the example 1 here. Example 1 here is actually based on the halfway rectifier. Okay, single phase halfway rectifier with resistive load, purely resistive load only. And then you want you to find those performance parameters like the efficiency, form factor, ripple factor, transformer utilization factor, PIV of the diode. PIV is peak inverse voltage of the diode. Okay, so you still remember you are using the probe just now I show you. Okay, you are using the probe, the oscilloscope or a meter. You measure it across the you measure the value across the diode. This is called the PIV. Okay, then we also have the F, the crash factor of the input current, and G, the input power factor. So all in all, in this example, because some of the value can be cancelled. For example, in this case here, the resistor R. Now, this question do not give you any value for the R. Okay, but you still can calculate the value for all those things. Okay, so this one is because later on you can see that your VM, and also your R, all can then be cancelled. Okay, common. Okay, and hence, for example, the part A here, before I can calculate the efficiency, I need to know what is my PDC and also my PAC. My PAC is my IMS power, output IMS power. Okay, so if the converter is lossless, your output IMS should be equal to your watt ampere rating, which is your VS times your IS. Yeah. Normally this is the way lah. Okay, so and hence you can see that if I am getting all those value here, VDC, IDC, VMS, and IMS, then I can calculate my VDC and also my output IMS hour. And hence from there, I can then start to calculate my efficiency. So efficiency is just the ratio of the PDC over your AC, right? So that will give you 40.5%, and you can see all the VM and also the arc is then cancelled. Okay, so part B form factor, it gives me 157%. So basically, you can also see that efficiency is low, form factor is big. That means that the size is actually bulky, larger. Okay, ripple factor, okay, is 121%, also very large, because we have a very high ripple appear across your output. We then in the part D, TUF, to do the TUF, you first need to find what is your supply voltage VS and your IS at your transformer secondary. Okay, so this one is actually based on this one here. Okay, that's why I say the transformer, if the system is come with a transformer, your secondary of your transformer value is in fact the input to your rectifier. Okay, so we don't need to care about the input, the primary. Yeah, we need to work out the VS and IS here in order to do the calculation. Yeah, and we also know that the supply current is similar to your load current in this case. Okay, half-wave rectifier, they are the same. Yeah, and hence you can see if I'm doing the integration for my supply current VS here, supply voltage VS here, I can see that my supply voltage at my transformer secondary is in fact equal to VM over SERT2. Okay, because at my transformer secondary side here, I have actually a full wave. Okay, my this part here is, sorry, my this part here is actually a sine wave. So it's actually a full wave. Okay, so that I have VM over SERT2, which is opposed to the load side here. The load side here, you have only VM over 2, because you only have one ripple per cycle. Okay, so that makes a difference. Yeah. Okay, then again, for the transformer secondary current, the IS is actually follow the load current. So your load current, based on the calculation, that will give you equal to 0.5 VM over R. So it will also follow this one. Okay, because current is in series. So your IS, which is your transformer secondary current, okay, supply current, is similar to your output current. Yeah, and hence, if I want to find the watt ampere rating for it, I should actually use this value multiplied by this value to give me the input watt ampere rating, and the TUF is the ratio of your PDC over your VA or VS IS. Okay, so in this case, you see that your TUF is having this value here. This value here, if you do 1 over TUF, that will give you the rating, the size. How many times of the size is actually required? Okay, so that means that if you are measuring for this half-wave rectifier, normally you get a very small value, and hence, yeah. the reciprocal will become bigger. Yeah. And then the part E here, the PIV. PIV normally is equal to the VM. Okay, for in this case, because based on our measurement here, you can see here, you can see this curve here, the maximum value is actually at minus VM. So that you can see the peak inverse voltage of your diode is equal to VM. Yeah. Then for the part F here, we need to find the crash factor. Crash factor is actually equal to peak over the IS value. In this case, your IS is equal to your load current, which is equal to 0.5 VMS over R, isn't it? So it's actually half of the value. Then if I'm using the ratio to using this over this one, that should give me 2. So that you can see the crash factor somehow is actually high. We have 2. Okay, for this type of rectifier. Then the power factor, the input power factor, because it is a resistive load, so we have the formula which is equal to your output IMS value or PAC here over the watt ampere rating. Just now the TUF is PDC over watt ampere rating, but power factor is your PAC over VA. Okay, slightly different. And then you can see your power factor is in fact equal to 0.707. Now, how to get this 0.5 times 0.5 over 0.707 times 0.5? Please find out. The answer is actually, I have already told you, is due to the difference of this voltage here. Okay. Yeah, you try to work it out. So far so good. Okay, you follow? Follow, can, good. All right. The next one is in fact with the IL load or the inductive load. Normally we call inductive load. Maybe we continue a little bit. Okay. So now what happens if the load now no longer just R, but is actually R and L connected in series together? What will happen? Now, as we know that, okay, inductor normally will not allow the current to change instantaneously, right? So normally you can see that if we have a inductive, normally, yeah, your this current waveform will be somehow lagging your this voltage waveform, so that basically we inductive load your this power factor normally is actually lagging. You're having a lagging power factor. But if you're having the capacitor, okay, maybe RC connected in parallel, then you have a leading power factor. Okay, but to certain extent, most of the load around in this this world here, mainly they are in fact a type of inductive load. For example, your motor. Okay, your dynamic motor, your load is also a type of inductive load, because inside the motor is actually the wire winding. The winding become the inductor. Yeah, and hence when you are doing some simulation or model of a given motor, you tend to use the inductor to model it. Yeah. Okay, so when I'm actually having this type of IO load here, and you can see that if I'm measuring the voltage VR here, and also my VL here, they are actually slightly different in between the two waveform here. And somehow you can see that because of the inductor here is a type of, is also a type of energy storage element. So during the positive half cycle, when the diode D1 is actually in forward bias, the current flow in this direction. So the inductor somehow you actually charge up the energy, you store the energy. Okay, you store the energy. Okay, but when during the negative half cycle, the negative half cycle is actually reversed. So it's actually blocked by the diode here. So the current of the inductor cannot actually go in this direction. But because of the negative half cycle is actually blocked, so this one no longer it cannot be actually conduct. But because of the energy store here, you actually force your this current to flow into the same direction like this before your this secondary side of your this voltage is actually larger than the energy that is actually produced from your this inductor here, and hence you actually force your this voltage to actually go beyond. Okay, the current the current to actually go beyond this one. Okay, and then when you are looking into the actual fact here, the voltage will actually go down to a negative part up until when it is actually finished discharge, then only then it go back to zero. Okay, so this is the effect of the inductor, and hence you create the angle called the extinction angle here. Okay, the extinction angle is somewhere in between pi to 2 pi. Okay, this extinction angle called sigma. This symbol is called sigma. Okay, this sigma here can be the value depend very much on the value of L. If the L is large enough, it may have a higher or bigger value of this sigma. And also it depends very much on the R as well. If you have a small value, so that you actually allow the current to the energy from your inductor here to discharge it slowly, and hence you also having a larger value of the sigma. Yeah, if this one is small, so it can actually discharge it quickly, but heat you actually need to be released faster. Otherwise, your this resistor here will actually heat up. Okay, so you also affect this one. Okay, so when you are measuring the voltage across your diode D1 here, you should measure, you should see that from pi to pi plus sigma here. Okay, you measure nothing because during this period of time, your diode is still under the forward bias. This forward bias is actually supply from the discharging of your this energy from your inductor L here. It's not from the supply. Okay, from this period from pi to pi plus sigma here. Okay, or pi to sigma. Okay, this period of time. Okay, is actually driven by the discharging of your inductor. Okay, and hence because of the forward bias during this period of time, you measure nothing. Okay, this point is still forward bias. So we already said earlier, if a diode is in forward bias, the diode, we can assume that it's just like a wire or just like a switch. Okay, turns on, then there will be no potential difference between these 2 points for ideal case. Okay, so you measure nothing, and up until this point, then only you measure something, because after the sigma here, your this energy for the inductor energy already discharged, finished, and then your supply is actually under the secondary second half cycle, so the current should flow in this way. Is to actually cause your this circuit to become reverse bias. Yeah, your diode become reverse bias, And when you reverse bias, only then you measure something. So you measure some sort like this. Okay. So if you are trying to work out the average output voltage, the VDC here, the VDC here, you have the integration from 0 to pi plus sigma, okay, which is from this range, from 0 to this range, okay. And hence, you can see that after derivation, you found that my VDC is equal to Vm over 2 pi times 1 minus cos pi plus sigma. Okay, then the load, the average load current is equal to VDC over R. Why? Where's the L? Can you tell me why? I'm having the IL load, but when I comes to the IDC here, my IDC here is equal to VDC over R only. Where's the L? Why we do not consider the L? Anyone can answer? Okay. We are not considering the L. It is because, as you can see, that for every cycle, the energy stored inside your inductor is actually discharged up, so that the average value of your inductor should be equal to 0, and hence to calculate the average only affected by your resistor R. Okay, but if we are talking about the instantaneous value, okay, the instantaneous current, then you need to actually consider the inductor L. But for average current or average value, normally the L will be omitted. Okay. This one is another one. I think this one is with a free wheeling diode. I think the time is there. I will continue. I'll continue. Maybe. Or do you want me to continue this? Finish this slide first. Can? You have time? Can? Okay. Good. All right. So you can see, without the inductor, then without the feeding diode here, the inductor will actually force your current to flow in the same direction during the next half cycle. Okay, before the inductor is actually finished discharging the energy. Okay, but what happened if we place a diode here? We place a diode across the RL, the IL load here. So if I'm placing this diode here, you can see that during pulse-up cycle, the current flow in this direction. This one become reverse bias, so there will be no current flow through here. All the current flow through in this way. Okay, same. And also your inductor L is actually charging up during this period of time. Okay, so up until when it is become a reverse bias, when it become a reverse bias here, yeah, your this supply current here should actually go into this diode DM here, and then but it also blocked by your D1. Okay, D1 become reverse bias. So all in all, the voltage waveform is not affected. However, there is some affection to your this part here. When during the next cycle, the energy of your inductor that is previously charged up, you'll be discharged through the diode DM here in this loop. So it keep looping until if it finish discharging. So with this diode DM here, you can see that the current will not flow back to the supply, to the supply in this loop. Okay, if flow back in this loop here, you can see that your waveform, your diode waveform will be affected. But with the diode DM here, you can see the waveform is actually restored. is actually restored. And also you can see that there will be no extinction angle. The extinction angle no longer there because the energy, the inductor energy is discharged through this LDM here. So you not kacau this the system, not like this one. Okay, not like this one. You create a negative voltage go down like this. Okay, but and also because of this negative voltage, you actually cause the waveform to be the waveform to be trimmed. Okay, but this one no. Okay, so it will be like this, and hence if we are adding in a diode, this diode here, this diode is what we so called the freewheeling diode. Freewheeling diode. If we have the freewheeling diode here, and you can see that for a given IL load, if you do the derivation will be actually exactly similar to the one in your resistive load only. Yeah, all the value is actually similar. Yeah, the VDC, VMS also the same. Yeah. Okay, so this make the difference. Okay, and then the application I think I will tell you later on. Okay, so far we just complete our first 20 slides for today. Okay, so the rest will continue on Monday class. Okay, also please take note that starting next week, it is better for us to have a physical class rather than the online one, and because this is the physical class is actually the university's procedure. Okay, they want us to have a physical class rather than through the online. Okay, last time people say too many online or get bored already, we need to have the physical one, but now you keep want to have the online one. I think it's not a good idea. Okay, yeah, so starting next week, yeah, we will switch to the physical one, unless there is anything happen like today. Okay, because I was having this close contact with the COVID-19's person, so I have to quarantine myself. That's why I agree that we are having this online class. Otherwise, I prefer to have this physical class with you. I want to see you physically rather than look at my computer screen. Huh? Okay, so I think that's it for today. Thank you for your attendance. Yeah, and please do some kind of revise on these chapters. Who is it? Okay, for the lab section, is maximum 3. Okay, I know that you have 11%, so that you're supposed to have how many groups? 3 groups of 11 and 1 group of 2%. Okay, so 332. 3332. 3332. Okay, so each of the section we have 2 groups attend the lab per week. So our lab should actually start on next Tuesday, right? Yeah, Tuesday. So next Tuesday, I will see you in the lab from 3 to 6. I believe your Dr. Yo's class already moved, right? There should be no issue, and our lab will start from 3 until 8, which is means that week 3, week 4, week 5, week 7, and week 8 we also have the lab sections. Okay, so week 3, say you have 4 groups, right? Group 1 and group 2 come week 3. Group 3, group 4 come week 4, doing the same thing. And then week 5, alternate back, group 1, group 2, do the second experiment. Week 6, 3 and 4, do the same experiment, second experiment, and then, and so on and so forth. Okay, so please be prepared, and you must have your lab menu with you, and then read first before you come in. Read first, meaning that at least you understand what you supposed to do, and then how you going to start, how to do it. Okay, because this one is hands-on, you have to do it yourself. I will be there to guide you, to check your secretary, and I will tell you whether it is correct or not. Okay, but you need to do all the hands-on yourself. Yeah. All right. So I think that's it for today. Thank you for attendance. Yeah. See you on next Monday. Okay. And also have a nice weekend. Bye bye.